All right, so 5.3, circular trigonometric functions. This is going to be, again, like I mentioned, where the fun actually begins. Everyone knows what an angle is. Everyone knows what an angle measure is. Now we can start applying it to some type of rigorous exploration. Okay, this is the chapter where the unit circle comes into play. This is where your geometric remembrance of soaking your toes in geometry. This is where SOHCAHTOA comes back in. Okay, let's define what a reference triangle is. A reference triangle is formed by dropping a perpendicular called an altitude from the terminal ray of a standard position angle to the x-axis. That is, again, the x-axis. Okay, by dropping we mean vertical. Okay, vertically. The reference angle is going to be just like the reference angle has always been. It's the positive acute angle between the terminal ray and the x-axis. So that hasn't changed. But we are going to create a triangle now. Okay. Now, if the terminal ray terminates in one of the four quadrants, we're going to actually have a triangle. If the terminal ray terminates on the x or y axis on one of the quadrantal angles, as we already know, there is no reference angle. It's undefined. It's not acute, and we won't have a triangle. But let's take a look at what happens if we look at each of the four quadrants. So go ahead and draw yourself a y-axis, snap a line if you want. Draw yourself an x-axis, snap a line. I'm just going to copy that so I can paste it. Let me just actually paste it right now. Paste, 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 paste. I'm reminding myself of my kindergarten years when that's all I ate. Paste, paste, paste. That was a joke. There was a kid that ate paste. Wasn't me, though. All right, if your angle terminates in quadrant one, so let's draw a little quadrant one angle. Boom, there's your terminal ray right there. There's your terminal ray. This angle is theta, right? How am I going to create a triangle? Well, here's what we're going to do. From anywhere on the terminal ray, let's say from right there, from that point x comma y on the terminal ray, we're going to drop a perp. That's a vertical drop, okay? Perpendicular means that it's at a 90-degree angle to the x-axis. That gives us this little triangle right here, which we call the reference triangle, okay? And theta, because it's in quadrant one, is also theta ref, right? We know that. So the only difference now is we're creating a triangle. We've already had the reference angle. Now, what's unique about using the point xy is that means that the width of the triangle is x and the height of the triangle is y, right? You go right x from the origin and you go up y. Got it? So there's your reference triangle in quadrant one. Theta is equal to theta ref. All right, what if your angle terminates in quadrant two? What if we have a quadrant two angle? Here's theta, right? There's theta. Is theta also theta ref in this case?
No.
No, theta ref is right here. There's theta ref. Now, to create a triangle, we could drop a perp from anywhere on the terminal ray. Anywhere on the terminal ray. Okay? And again, this is the point xy. X is going to be negative, y is going to be positive. The absolute value of x is going to be the width, and the absolute value of y is the height. We create a little triangle again. There's a little triangle. What's that triangle called? It is a right triangle. What's it called? That's your word of the day. Reference triangle, right? Reference triangle. And the reference angle is always going to be the positive acute angle of your reference triangle. Okay? Now, let's review. How would we find theta ref in this case? Theta ref is not equal to theta. It's what? Pi. How do we find it? It's pi minus what? Theta. Good. It's pi minus theta. Because we stopped short of pi. We're not using degrees anymore. We stopped short of pi. Pi's over here, right? So by how much did we stop short of pi? Well, pi minus theta. That's how we find the reference angle. Okay, quadrant 3. If we go all the way around to quadrant 3, here's the terminal ray. Here's the point on the terminal ray. Call it x comma y. Now we're dropping a perp vertically, like that. Oops, that didn't work. Drop a perp vertically by drawing it upwards. Okay, we can draw it upwards. That's still a vertical motion. Here's your reference triangle. Are theta and theta ref the same? No. Here's theta. Theta is between pi and 3 pi halves. Theta ref is this right here. How will I find theta ref? Is it theta minus pi or pi minus theta? Theta minus pi. Because now theta is bigger than pi, yeah? Over here it was pi minus theta because theta was smaller than pi. And why does it matter if we do one minus the other or the other way around? What do we know about the reference angle? It's always what? It's always positive. So it's our job to make it positive. All right, and then if we have a terminal ray that terminates in quadrant 4, there's a quadrant 4 terminal ray. I drop a perp from the x-axis or to the x-axis from a point on the x-axis. And, oh, by the way, this was x and this is y again. Hey, good morning. So here's your reference triangle right here. I don't need it. You keep that as a souvenir. There's your right angle. Here's x and here's y. And let's see, theta is the angle that gets us all the way around. And of course, theta ref is just this one right here. How do I find theta ref now in radians? 2 pi minus theta. Very good. Now I'm stopping theta ref short of a full rotation, which is 2 pi. 2 pi is all the way around. Good. All right. So we've already been finding reference angles. We know how to find reference angles. The only difference now is we're going to create these triangles that have side lengths. And the side lengths are determined by the point from which we drop the perp. Got it? Okay. Now that we have triangles, triangles have how many sides? 3. Let's go ahead and label them. The horizontal is always going to be x. X is always the horizontal, or the width of the triangle. Always. Okay? This is why we put it in standard form. X is always the horizontal dimension or the width. Y is always the vertical dimension or the height. Now there's another side to this triangle called the what? Hypotenuse. The hypotenuse. Guess what letter we're going to use for hypotenuse? R. Very good. No one said R. C, I heard. When you do the Pythagorean theorem, I know you do a squared plus b squared equals c squared. So C we've used in the past for hypotenuse. Hypotenuse starts with the letter H, so I can see why you would say H for hypotenuse. But we're going to use R. Why R? What if I were to take that point? Yeah, R is the hypotenuse, which is also your radius of rotation. If I were to take that point xy, which is r units away from the center, and I were to continue rotating all the way around, it would make what shape? A circle. And r would be the what of that circle? The radius. Good. All right. So the hypotenuse is going to end up being just the radius of this circle. Okay. So we have x, y, and r. Now the hypotenuse being r and the horizontal and vertical being x and y, those are the two short legs of the right triangle. We get this relation between them: x squared plus y squared equals what? R squared. Instead of a squared plus b squared equals c squared, x squared plus y squared equals r squared. That's just the what theorem? Pythagorean theorem. Yeah, it's been around a long time. The Pythagorean theorem. So that gives us a relation between x, y, and r. That's pretty cool. All right. So let's go ahead and talk about a trigonometric function. We're defining now a trigonometric function. You ready? A trigonometric function is a ratio of 2 of the 3 sides of the right triangle formed by the reference triangle, okay? Whose reference angle theta ref is determined from the independent angle theta. So theta is your independent variable. Theta is your independent variable. You can start on the positive x-axis, and you can rotate counterclockwise in the positive direction or clockwise in the negative direction, and you can rotate as much as you want or as little as you want, but whenever you stop, you're going to land hopefully in one of the 4 quadrants. You can land on the axis. We'll talk about those in a little bit. But if you land in the interior, now you drop a perp to the x-axis, and you have a unique triangle that's formed by the rotation, right? And I just drew them all at 45 degrees. You could actually have an angle that looks like this, right? And drop a perp down that looks like that. Or you can rotate up here and have a triangle that looks like that. So your triangle can actually be wide and short, or it can be narrow and tall, right? Or maybe equal in the middle. But wherever you decide to stop rotating, you're going to get a triangle that's uniquely shaped. What is the trig function? Don't ever forget the basic definition of a trig function. It's a what? It's a ratio of two of the three sides. That's it. You pick any two of the sides, x, y, and r, and you divide one by the other, and you got yourself a ratio. Let's come down here in example 2, and let's just copy and paste this. We don't want to redraw it. Let's just copy and paste this diagram from part A up above. Copy and paste. Boom. And I have part of my circle there. I guess I can clean it up. There we go. Get rid of the dotted lines from the circle. There we go. Let's go ahead and list as many ratios as we can, taking two at a time. Can someone give me a ratio of xy to r, or r to x, or y to r, anything? What? I'm just looking for a ratio, any ratio of two of the three sides. X to y. Now, when we say x to y, that's another way to say x colon y. That's another way to say it, right? Or we say x to y like that. Those all mean the same thing, don't they? X to y, x colon y, or x divided by y. We're going to look at the ratio as a division process, okay? So you said x to y. I'm going to go ahead and I'm going to write x to y. I'm going to write that down here in the bottom right. Yeah, I heard it wasn't good. Are you all right? Okay. X to y. X to y. Ryan just walked in, so Ryan's going to watch the video that we're recording right now, up to the point right now where we say, hello, Ryan, and then he can stop. Ryan, stop the recording now unless you just want to keep watching. But you've watched it up to here. You've listened to everything that you've missed. All right. X to y. That must be the only one, yeah? Okay. What? Because I'm thinking of another one? I don't know. I don't know. I'm dumb. I'm just asking y'all. That's why I asked y'all. Did anyone come up with another one? R to X? Oh, R to X. I'm going to put that one right above there. R to X. Good. I like R to X. So those must be the only two. Y, hang on. Y to R? I heard Y to R. I'm going to put that one in the top right, top left. Y to R. R to Y. R to Y. I'm going to put that one over here on the top right. R to Y. Okay. So that's 4. That must be all of them, huh? X to R. I'm going to put that one over here in the middle on the left. X to R. Y to X. I'm going to put that one here on the bottom left. That must be all, right? That's 6. Are there any more ways to write them? These are called permutations. How many permutations can you have of 3 objects taken 2 at a time? 6, right? Yeah, 6. Yeah, there's 3 ways for the first, times 2 ways for the second. 3 times 2 is 6. We've got, those are all 6 of them, all right? So I claim that these are the only ratios that you can take for this given triangle that's determined by our unique choice of theta, right? Now, we're going to be referring to these ratios by name, but I don't want to just say, hey, you, y over r. Hey, what's up, r over x? Hey, y over x. We want to give them names. So back in the day, when the names were first being assigned to these guys, I wasn't there. I might have put forth the name, can we call one of them Chuck? Can we call one of them Penelope? Can we call another one Brian? I don't know. I would have given them names like that. Or maybe I would have suggested cute names like, can we call one of them Cannoli and another one Linguini? Can we just name them all after pastas? I wasn't at the meeting. Someone else came up with the names, and we're stuck with the names for posterity. So the top left, the name given is sine. Okay, that's the sine ratio. Okay, they called it sine. Now, because it's a function of theta, we abbreviate the word sine, S-I-N, and to show that it's a function of our independent choice of theta, we put a theta behind the S-I-N, and we read that as sine of theta, right? Like f of x. Theta is your independent variable. Got it? We can rotate wherever we want and stop. That's our independent choice of theta. It's like our x, it's our input. And then the output itself is the ratio of the vertical to the hypotenuse. Yeah? Okay. The name given to the one below it at the meeting that I was not at is cosine. And we abbreviate that one COS, and then we put the of theta behind it. So again, theta is your independent variable. It's like your x. And then, ooh, is the picture bad? Is it totaled? Did he back into it 100 miles an hour?
No, it was.
He just tapped it?
Yeah.
Did you have to get police over there to make a report?
Yeah, I did.
You did? Yeah, good. Yeah. All right. Guess what name was given to the bottom left one? Y over x. Tangent. Yeah. Tangent. We abbreviate that one tan of theta. Tan of theta. Now, it's interesting that we really have two names, don't we? We have sine and tangent, and then the middle one was cosine. Someone just took co in front of sine, right? You might have thought that the bottom left one then would have been cosine, right? Instead of tangent. We got sine, cosine, 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 cosine. But they didn't. They stopped with just one co. They stopped with one co. Because it would get confusing, right? How many co's are in that one? 12? 12 co's, right? So they said, one's enough. Sine, cosine, we can remember that. And then how about a guy in Britain that lays on the beach too long? What's that? Tangent. Okay, let's call it tangent. All right. Hey, and then they got, well, anyone have an idea for another name? We got sine and cosine. How about tangent and cotangent? And they were like, yeah, that's awesome. So there is another one named cotangent. That's the one in the bottom right, cotangent. You probably haven't heard of these other three names because they didn't show up in geometry. But you got cotangent. And guess how we abbreviate cotangent? No, it's a three-letter abbreviation. No. C-O-T. It's just the first three letters. Cot. Cot stands for cotangent. And of course, just like the others, we put an independent variable there and we put an equal sign. So the cotangent ratio is the reciprocal of the tangent ratio. Are the sine and cosines reciprocals of each other? No, they're not. What's up with that? This is some squirrely labeling, right? I like tangent and cotangent being reciprocals of each other. That's easy to remember, right? Tangent is y over x. Cotangent is its reciprocal, x over y. Does that work for sine and cosine? Sine is y over r. Cosine is r over y. No, it's x over r. We should have just named them after pastas. Spaghetti, cannoli, ZT, pen. But we did it. Now we need. I think we only need one more name, because if we can come with one more name, then for the final name we could just say co and then that name. How about operate? Can we have one of them called operate and the other one can be cooperate? No, that's no silly. That's what the other name is. Secant. Secant. So we call the middle one over here on the right secant. That's the full name. And guess how we abbreviate secant? S-E-C. And we put of theta. It's a function. Remember, these are not just ratios. They are functions of theta. They are ratios determined by the triangle that is uniquely determined by your choice of theta. X could be big and Y could be small. X could be small and Y could be big, or they could be roughly the same size, like the way I drew it. Now, of course, then, what do you think the top last one right on the right is? Cosecant. You are correct. And guess how we abbreviate cosecant? We can't just go COS, can we? Because that's cosine already. So we use ZPN. ZPN, right? I'm kidding. We don't use ZPN. Did you always start writing it down? No, that doesn't make any sense. But we do something that does make sense. CSC, cosecant, cosecant. Okay, and we call it of theta because it is a function of theta. And that's it. Your first job today, before you go to sleep tonight, is to memorize the name and definition of all 6 of these trig functions, right? Now, remember that you learned SOHCAHTOA as well, didn't you? SOHCAHTOA. Does SOHCAHTOA still work? It does. Look at the sine ratio. If this was your reference angle down here, this was the opposite. This was the non-hypotenusal adjacent. And of course, this is the hypotenuse. So in terms of OA and H, instead of X, Y, and R, what would sine be? It would be opposite over hypotenuse. Well, the opposite is Y, and the hypotenuse is R, isn't it? Yeah. Okay. The sine measures the vertical ratio. If you want to remember sine, measures your vertical ratio. It measures the height. Sine measures the height with respect to the radius. Here's an easy way to remember sine is height. They both have the same long I sound. Sine, sine, height, height. And it's determined by the y variable. Sine, y, height. Got it? Sine, y, height. Sine measures the height of the triangle, and it's determined by the y value. Sine, y, height. Got it? Yeah. Won't forget it. Now, cosine is adjacent over hypotenuse. But when the adjacent is x and the hypotenuse is r, it's x over r. Right? So cosine measures the horizontal. Whoa! Cosine measures the horizontal, which is the width of it compared to the radius. And it's determined by the x. Now, there's really no way to remember that like there is for sine, y, height. Cosine, width, x. Doesn't work that way, right? Cosine, width, x, they all have different sounds. But sine, y, height, you can remember. And then cosine would be the other one. So which of those two measures the height? Sine measures the height. And which one measures the width? The other one, cosine. Sine and cosine are your two main fundamental ones. Sine and cosine are your two main fundamental ones. If you had to put a third guy into that group, tangent would be the next one. Tangent measures the ratio of y to x. It doesn't measure it with the radius as a baseline. And then you have the reciprocals of those three main ones. What's the reciprocal of sine? Cosecant. Do you see why I wrote the ratios like this now? Because they pair up left to right as reciprocals. What's the reciprocal of cosine? Secant. What's the reciprocal of tangent? Cotangent. Now that's the only one right now that you think makes sense. Why didn't we call the reciprocal of sine cosine? And why didn't we call the reciprocal of secant cosecant? Because co does not mean reciprocal, believe it or not. Co stands for something else. Co actually means cofunction. We're not ready to understand what cofunction means yet, but they are related by the name sine and cosine, tangent and cotangent, secant and cosecant. They're cofunctions of each other. Right now, you just have to memorize the reciprocal pairs. And tangent and cotangent are the only cofunctions that are also reciprocals of each other. Let's try it without looking. What's the reciprocal of tangent? Cotangent. And what's the reciprocal of cotangent? Tangent. What's the definition of tangent in terms of x, y, and r? We don't want to do SOHCAHTOA. You don't say opposite over adjacent, because that's when you're on the Euclidean plane. We're on the coordinate plane now. What's the definition of tangent? Y over x. You got to memorize that. That's got to be second nature, just like what's 2 times 5? 2 times 12? No, 11. No, I'll get in there. 9. Oh, shoot, 10. 2 times 5 is 10. We know that. What's the definition of tangent in terms of x, y, and r? Y over x. So then what would be the definition of cotangent? X over y, because they're what's of each other? Reciprocals. All right, without looking, what's the definition of sine? The definition in terms of x, y, and r? Y over r. Did you say x when I said sine? Sine, y! Height! I don't say sine x, right? It's sine y height. What's the definition of sine in terms of x, y, and r? Y over r. Y over r. Sine is y over r. You got to know that. Don't tell me that it's opposite over hypotenuse. I don't care about opposite over hypotenuse anymore. I want to know what it is in terms of x, y, and r. What's the definition of sine? Y over r. Sine y over r. Got it? What's the reciprocal of sine? It's r over y, and its name is what? Cosecant. Cosecant. What's the name of the reciprocal of sine? Cosecant. And what is cosecant in terms of x, y, and r? R over y. It's the reciprocal. Okay, good. And then the last one. What's the definition of cosine in terms of x, y, and r? X over r. And what's the name of the reciprocal of cosine? Secant. And its definition is what? R over x. There you go. I just helped you memorize them. You need to memorize them in terms of x, y, and r. If you don't memorize those in terms of x, y, and r, then as we move forward and we start getting more and more complex, and we start learning the unit circle, you're going to be like, I'm lost, sir. And I'm going to be like, what's the definition of cosecant? And you're going to be like, I don't know. And I'm like, well, there you go. You led yourself astray there. You're not lost. You wandered off, buddy. Good luck finding your way back. Got it? What is the definition of cosecant in terms of x, y, and r? R over y. Yeah. And secant's what? R over x. But cosine is what? X over r. And tangent, of course, is what? Y over x. And sine? Y over r. Good. And then cosine is what? X over r. And cotangent is what? X over y. I hope you're doing that without looking. You need to memorize those. There are flashcards. If you go to Quizlet, you can look up trig functions, trig ratios, and you can quiz yourself on that. If you need to, make your own Quizlet cards. In fact, get yourself 6 3x5 cards and make your own. It's not that hard, right? Go old school. Go analog. But memorize them. In fact, if we were coming back to school tomorrow, I would quiz you over those. So I should probably quiz you over those first thing Tuesday morning. Yes. Why wouldn't I want to give you free hundreds? After a 4-day weekend, you think you're going to forget sine, y, height? No. You will not forget that the rest of your freaking life. A cop's going to pull you over and he's like, excuse me, did you not see the stop sign? And you're going to go, sine, y, height! And the officer's going to be like, oh my gosh, you got a little PSD there. PTSD, I see, buddy. You must have had a good pre-cal teacher. I'm going to let you go. You've suffered enough. All right? You got it? Sine, y, height. All right, here they are in a box. These are derived from the rotation of an angle that if we were to go all the way around would again make what shape? A circle. That's why these are called circular trigonometric functions. There are other types of trig functions out there. You have hyperbolic trig functions, which are pretty useful when you study later higher level calculus. There are elliptical trigonometric functions, okay? There are other trig functions out there that are defined from other shapes. These are defined from a circle who's centered at the origin, whose radius is the hypotenuse of a reference triangle. Got it? All right. Let's see what types of fun we can have now with these new trigonometric functions. I call these types of problem the 2 clues problems. Did you ever watch Blue's Clues growing up? Good. Who did it, right? Steve went off to college, right? He had to go deal with his drug problem, right? And they got a new host, and it wasn't the same after that. But Steve came back later. Oh, whatever. Whatever. The rumor was always he had drug problems, but Steve was good. Steve was good. I learned a lot from Steve, right? I call these 2 clues problems, and you can think of them as Blue's Clues problems because there are going to be 2 clues, and from these 2 clues alone, what did Blue say? Blue skidoo, we can too? Yeah. We're going to be able to find out all this other information from just 2 clues, all right? Let's look at example 3. If sine of some angle theta is 5, 6, okay, there's your first clue. That's clue number 1. I know that the sine y ratio of some angle theta in standard position on the coordinate plane is 5 over 6, and 90 is less than theta is less than 180. There's your second clue. That's actually a big clue, isn't it? This clue tells us 2 things. Our angle is in what, Andrew? Degrees or radians? Hang in there. No, it's in degrees. Hang in there. It's in degrees because it's between 90 degrees and 180 degrees. So I know it's in degrees. Secondly, it actually tells us what quadrant we're in, right? What quadrant is between 90 and 180? Quadrant 2. So it tells us 2 things. This one clue tells us 2 things. Our angle is in degrees, and it's in quadrant 2. Okay. From those 2 clues and those 2 clues alone, here's what we're going to be able to do. We're going to be able to find the simplified exact value of the other 5 trig functions of theta, and then using a calculator, we're going to be able to find theta and theta ref. Got it?
Got it.
Got it. All right, here's how we do these problems. Step 1, draw a picture. Draw a picture. That's a big bird. That's a pterodactyl, baby. And it's far away. Imagine if it were closer. This is not the kind of picture that's going to help. Okay. What we're going to do is we're going to draw the angle itself in standard position. What quadrant does it terminate in? Second. Now, if you're going to draw a terminal ray in quadrant 2, you can draw it anywhere in quadrant 2. You can draw it closer to the y-axis. You can draw it closer to the x-axis. I would recommend just drawing it at the 45-degree angle. Because as long as you're in the right quadrant, where you are is not really as important. So give yourself as much room to write by not limiting yourself on either side of it between the x and y axis, okay? And then draw your arc. This is theta. There it is, okay? Now, I need to create a reference triangle. How do I create a reference triangle? I drop a perp, right? Like a New York cop on the streets chasing the bad guy. They tackle him and they drop the perp, right? Perp is down, need assistance. We drop a perp. And that creates ourselves a little what? Little triangle, yeah. And here's the reference angle right here, theta ref. It's the positive acute angle of our reference triangle. So it's almost like we created a little house, right? The little right angle can be like the door. We put a little chimney right here. Little triangle house, right? Yeah, kind of. All right, now, here's where the second clue. I've used kind of the second clue already to put it in quadrant 2. The first clue said that sine is 5 over 6. Let's write that down. Sine of theta, okay, is 5 over 6. What's the definition of sine in terms of x, y, and r? Y over r. Y over r. Y over r. So here's what we do next. We label the 2 sides of this right triangle based upon that ratio. So I'm going to call the sine, which is y, 5 over 6. I'm going to label the 2 sides. Is that true? If I had those 2 sides and I asked you what sine of theta is, you would say sine of the angle theta is the y to the r, that's 5 to the 6. 5 to the 6. Now, what if the point was further out? What if we dropped the point from way out here and it were actually 10 and 12? What would the sine ratio be if the triangle was bigger? It would be y over r. But what does 10 over 12 simplify to? 5 over 6. Yeah. That's why it doesn't matter the point from which we drop the perp to create the triangle, because the scale factor will always divide out. If the triangle is 3 times as big, then the 2 side lengths are 3 times bigger, and that scale factor divides out. Does that make sense? So we can always just draw it in the simplest form. We can always just say, I'm just going to drop it and label it as 5 over 6. Now, I'm curious about this side right here. Dang it. If only I knew what the third side of the right triangle was.
Oh, you do the Pythagorean.
Great! Pythagorean theorem. The Pythagorean theorem gives us a way to find the third side of a right triangle if we know the two other sides. And it doesn't matter which two we know, correct? So let's go ahead and do that. The P theorem. In terms of x, y, and r, it's x squared plus y squared equals r squared all the time. Yeah, yeah? Let's plug in what we have. We're going to get x squared, which is x is unknown, plus parentheses 5 squared equals parentheses 6 squared. And now it's just a little bit of algebra, isn't it? X squared plus 25 equals 36. So x squared equals 36 minus 25, which is 11. And now remember this is muy importante. You know what I was getting at, right? When we take the square root of both sides, we can't forget to remember plus or minus. Now, in geometry, did it make sense to have a side length that was a negative number in geometry? No. I'm not going to give you a board and say, here, go cut me negative 2 feet. You're going to be like, say, what? You want me to make it 2 feet longer? That's kind of what it would amount to, right? A negative length? We don't have negative lengths. But guess what? On the coordinate plane, we can have negative lengths because the negative just tells us the direction, not the size. So once we do plus or minus, I need to figure out which one I want based upon the quadrant I lived in. To get to this point xy, I have to go from the origin. I have to go left, don't I? And up. If I have to go left, that means x is actually what? Negative square root of 11. Yeah. And so this point xy now that's in space is actually the point negative square root of 11, comma 5. That's the ordered pair. That's out there in quadrant 2. Negative square root of 11, comma 5. When you find the third side, you want to make sure that if it's x or y, we'll say something later about r. In fact, I'll say it right now. X and y may be plus or minus, but r is always positive. He's a good guy to have as a friend in your corner. He's always positive, right? You're having a bad day? I'm having a bad day, R. Cheer up, buddy. There's always a silver lining. At least your shoes are tied and you're not tripping. Man, you're always positive, R. How do you do it? How do I tie my shoes or how do I stay positive? Both. X and Y can be negative depending on the quadrant we live in. Yes? But R is always positive because it's just a radius of rotation. It points out in a positive direction from the origin, and you can rotate it however you want to get into any quadrant. Okay. So now that we have all three sides, can't we list all 6 trig ratios? Yeah. Let's go ahead and get the complete set. Let's go ahead and set ourselves up for success. We'll start with sine of theta, even though it was given. I got sine of theta, cosine of theta, tangent of theta. If you want to set it up the same way every time, you're going to help yourself reinforce the reciprocal nature. So sine, cosine, tangent. That's SOHCAHTOA. Yeah? We do those 3 first. Now, let's list their reciprocal pairs off to the right-hand side. What's the reciprocal of sine? Well, what's the name of it? Cosecant, which we abbreviate CSC. What's the reciprocal of cosine? Secant, which we abbreviate SEC. What's the reciprocal of tangent? Cotangent, which we abbreviate COT. Okay, so this is my preliminary step. Setting up the 3 main ones, sine, cosine, tangent, SOHCAHTOA, and then the reciprocal pairs lining up in the rows, cosecant, secant, cotangent. All right, now if you want, especially in the beginning, you can write their definitions there. Sine is y over r, cosine is x over r, tangent is y over x, cosine is, or cosecant, sorry, is r over y, secant is r over x, cotangent is x over y. If you need to do that at first to help you reinforce the definitions, that's fine. Now all you got to do is pluck the values off of your reference triangle. Pluck the values off of your reference triangle. Let's do that. What would the sine ratio be? Just from the triangle, not from the given. It's y over r. What's y over r? 5 over 6. Is that what they gave us? Is that the same value that we started with? Yeah. All right, now what's cosine? It's x over r. It's what? Negative square root of 11 over 6. 6. The radius is the hypotenuse, 6. What's the tangent? Why? It's 5 over negative square root of 11. Now, here's what I want you to do. Anytime you get a negative in the denominator or a radical in the denominator, I want you to rationalize the denominator. Okay? That means multiplying by the square root of 11 over the square root of 11. That's equivalent to 1, isn't it? All right? What that's going to do, it's going to get the radical out of the denominator. Okay? You're going to get rid of the rational exponent. So we get negative. The negative could be in the top or the bottom now. Negative 5 square root of 11 over 11. You can pull that negative out front or you can put it in the top. Because the bottom is negative, the whole ratio is negative. So negative 5 square root of 11 over 11 is what we prefer. Okay? I'm not going to count it right if you put 5 over negative square root of 11. I want you to get in the habit of rationalizing your denominators. Okay, maybe I'll even draw a line here to separate them. I have my three main ones. Katoa. Sine, cosine, tangent. All right, what's cosecant? Don't do this. Don't just flip the ones you have in the left column. Go ahead and force yourself to pull the ratio off of the triangle and then compare it to the reciprocal. What would cosecant be from the triangle? What's r over y? 6 over 5. Now, compare it to sine. Is 6 over 5 the reciprocal of 5 over 6? Yes, that's how you want to do it, okay? What's secant? Secant is r over x. What's r over x? 6 over negative square root of 11. Now, I'm not going to leave it like that, but real quickly, is that the reciprocal of the cosine? It is. Now, I do have to tidy this one up. I need to multiply by the square root of 11 over the square root of 11, which gives me negative 6 square root of 11 over 11. Now, here's what's also going to be cool. You're going to get so good at rationalizing the denominator, you're not going to need to show me the step of multiplying by root 11 over root 11. You're just going to say 6 over negative root 11. Ah, that's negative 6 root 11 over 11. I hope you're going to be able to do that. You don't have to show me this step. Okay, let's actually say that. No need to show this. Unless you absolutely need to. Okay? Sehr gut. And then finally, what's x over y? Negative square root of 11 over 5. Now, is that the reciprocal of tangent before we rationalized it? Yes, before we rationalized it was 5 over negative 11. Now it's the reciprocal, and we don't need to rationalize that one. So, do we have all 6 trig ratios? Yeah. So that's why it was a fun twos clues problem. We had 2 clues. We had 1 trig ratio, and then another clue that told us where it lived. And from those 2 clues alone, we were able to extract all 6 of the trig ratios. All 6 of them. That's pretty awesome. Now, we're not going to have time today, but now that we have the 6 trig ratios or the 6 trig functions, using any one of the 6, these are like equations now with one unknown, I can solve for the missing unknown. If I have sine of theta equals 5, 6, theta is the unknown, isn't it? With the help of the calculator, I can actually find the angle theta. And of course, once I have theta, I can find the reference angle. We're going to do that on Tuesday. Be prepared for a quick quiz on Tuesday over the names and definitions in terms of x, y, and r of your 6 trig functions, okay? All right. Good day today. One last time for the recording. Sine, y, hey. Got it.
9.